Greetings, Physics 111 students. I'm going to make this one here to help you out with Unit 4-3, numbers 4, 5, and 6. So number 4 is about a sprinter, which accelerates from rest to 11 meters per second in a given time frame. So, like always, start this with a picture. We have a sprinter with a velocity in picture 1 here of 0. However, they are accelerating. All right, so crummy picture, but better than nothing. So in picture 2, they have some number here, and a delta t is given in the problem. So part A, to calculate the work, you can get that from the work energy theorem. PE1 plus KE1 plus work equals PE2 plus KE2. And what we can do is just take note, there's no vertical changes or springs or anything in this problem. We'll just datum out all the potential energies. And they started from rest. So it should be hopefully fairly obvious how to get the work. Okay. Number 2, calculate the power. All right, so power is change in energy over change in time. It's also equal to the work done over the change in time, because the work and the change in energy are the same thing. So that should be enough to calculate the power. Part C, if the sprinter converts mechanical energy with an efficiency of 25%, at what rate is he burning calories? So power-wise, there's kind of two things to consider, right? You've got the, let me say, the output power, which is the rate that the kinetic energy is changing. And that's what you're calculating here. But then I want to talk about an internal power here, the rate at which the person is burning energy. Okay, and if they are only burning energy at a 25% efficiency, that means their power output is only 0.25 of their, I'll say, power input, this being the rate at which they're burning calories, right? So you're going to use this value here and calculate that. That should get you rolling on that. I'm noticing too, by the way, the units say this. Calories per second with a big C. That's a kilocalorie, keep in mind. And just a little reminder, 1 kilocalorie is 4186 joules. I suspect you're going to need that conversion in that problem. Kind of sneaky there, the big C against the little c. Let's see here. Number 5, let's discuss. A woman cheats on her diet. Well, everybody cheats on their diet. But in this case, it says a 60-kilogram woman cheats on her diet and eats a 585 big C calorie jelly donut. So your number could be different, but we've got 585. It's a big C, so I'm going to put that's kilocalories. First thing I'd probably do is convert that to joules. You're probably going to want that in joules. All right. Actually, that's part A. How much energy is associated with that for part A? Okay, in joules. Part B, how many flights of stairs would she have to do to go through one donut, assuming 0.15, assuming 15 centimeters per stairs. So probably what I would do is kind of attack this from a work energy standpoint. 1, 2, write out the work energy theorem. And basically what they're saying is, all right, how many stairs? So I'm going to start with how high does this person need to go so that they do an amount of work equal to this. All right, so datum out your PE1. We're just going to assume moving up the stairs at relatively constant speed, so these are the same. And then you're going to take this number in joules, use it for your work term, and here you're going to have an MGH, and you can solve for H. Then they tell you 15 centimeters per stairs. That will allow you to calculate how many stairs. Now, there's a huge assumption here, though, that I've built into this, and that was assuming basically calorie burn for calorie work done, which is not how it works. If this person wants to walk up these stairs, you know, again, we're going to talk about this a little later here in another week, but a person is essentially an engine, what's called a heat engine. And let's say that, just to make the math super easy, let's say that this difference here in height represents 100 joules. Now it's going to be more than that, but let me just use that. Well, that means the person's going to have to do 100 joules of work, but the person will no doubt have to burn a lot more than 100 joules to do that, because no engines are even close to 100% efficient. A human being, to my best of my knowledge, is around 20% efficient, meaning to do 100 joules of work, they would have to burn about 5 times that, about 500 joules in calories, right? Because what happens is, as they're doing work, everybody who's exercised, you get hot, you start giving up a lot of heat, and you're burning energy in the process. So for part C, they're basically saying now to factor in a 21% efficiency. Now, what does that mean? Well, let's say that your change in energy internally and your work that you do, if you are 100% efficient, your change in internal energy would equal your work done. Change in internal energy meaning you're burning calories and dropping in energy. But if you're only 21% efficient, then the work done would only equal 0.21 times that change in internal energy. Use this to calculate your change in internal energy to see how many calories you actually worked off. All right, that should, I think, get you by number 5. Let's chat about number 6. Let's see, an aluminum bar raises by 10 degrees. I would start this with a picture, an aluminum bar, even just a super quick picture, aluminum, okay? And we have a temperature change, so put those in the problem. I assume it's going up 10 degrees. And there's an amount of heat absorbed that's given in the problem, and the mass is given. So this is just a basic specific heat question. So you start by writing out, all right, Q equals MC delta T. Anything having to do with specific heat, you're almost certainly going to need this. Given in the problem, given in the problem, given in the problem. Right? So there's just one thing left to do with that. So that should get you through that, no doubt. Hope that this helps. Have a great day.